Hi APE students, welcome to the solar insolation pre-lab. Let's go ahead and get started. First of all, the purpose of the lab, we are trying to measure the amount of solar radiation that strikes the surface of the earth per unit area. In our model, we'll be using a blank piece of paper to represent the surface of the earth and a flashlight to represent the sun. So there's kind of a brief overview of the methods that we're going to be using to perform this procedure today, and let's kind of take a deep dive into how that procedure is going to look. So the first thing that we're going to do is make a conversion factor by calculating the mass area relationship of a known something that's easy to measure the area of. So you'll be taking a 10 by 10 centimeter square, cutting it out and massing it. And we want to convert those centimeters to meters. When I look up a reference value for the energy per unit area that strikes the surface of the earth, it's usually expressed as watts per meter squared. So that's the unit we're going to use in our calculations. It's easiest when you do that conversion to first convert your centimeters into meters, as you can see I've done here. So my square is 0.1 meters on each side, and 0.1 meters times 0.1 meters is 0.01 meters squared. If I mass that piece of paper and find that it weighs 0.8 grams, I can write that conversion factor in two different ways. 0.8 grams over 0.01 meters squared, or I can flip it and have a true and accurate conversion factor. I decide which of those I'm going to use depending on what unit I'm starting with and what unit I'm going to. We'll come back to that in just a minute. So when you go to draw your ellipses, you can see on your data table that you have both a flashlight angle and an earth angle. You're going to tape a pencil to the flashlight so that I'm always measuring the distance above the surface of the earth accurately, that the distance of my sun from the earth doesn't change. If, for example, my flashlight is straight up and down, on my protractor, that's a 90-degree angle, and that corresponds to 0 degrees earth angle, or at the equator. When I start tilting my flashlight, you want to tilt it so that the pencil is on the outside like that, and I can get that tilted down as far as possible so that the location of the pencil isn't impeding my ability to angle my flashlight. So kind of play around with it before you start drawing any of your ellipses. When I get that angle as low as that flashlight as low as I can possibly get it, I'm not going to be able to get it all the way flat like it would be at the poles or what would be a 90-degree earth angle. So the greatest angle you'll be able to have will be an 80-degree earth angle. When I turn the flashlight on, and again, before you start measuring, you can play around with this, you are going to be measuring the outside greatest area of that ellipse that is formed by your flashlight. And the key thing is that you're measuring very consistently. We'll be turning the classroom lights off in the room while you're shining your flashlight or the sun is striking the surface of the earth, so you can have a nice accurate measurement of your ellipse. The next thing I want to do then is take those conversion factors I make. You're going to have ellipses that are everything from pretty small in size, where the sunlight is very concentrated at the surface of the earth, to at the poles, where I have a 10-degree flashlight angle or an 80-degree earth angle, where that energy is spread out over a very large area. It's not going to be easy for me to calculate the area of this ellipse like it was for my nice, neat square. So I'm going to mass this ellipse. Make sure that you label them with your earth angles. I don't really care about that flashlight angle after I've done my measurements. Label it so you can keep track of them. Mass it. And let's say, for example, I determine the mass of this ellipse to be 0.03 grams. That I have to use the conversion factor where grams is on the bottom of my conversion and area is on the top. So I'm going to convert the mass of this ellipse to an area. And then we want to know the amount of energy per unit area. So we're going to assume a nice round number of 100 watts of energy from the sun divided by my area. And I will convert that into the number of watts per meter squared. I'm then going to create a graph of my data where I have the angle of the earth which actually corresponds to latitude, corresponding to my variable of watts per meter squared. Good luck. See you in class.